All right, hello everyone, and welcome back to these astronomy talks. So we're now done with talking about stars, but we are reaching the end of these astronomy talks, which is very sad. But before we reach the end, we'll spend quite a bit of time talking about galaxies. And just like when we started talking about stars, we started with our own sun. We're going to start talking about galaxies, and we're going to start with our own galaxy, the Milky Way. So tonight's quote is from a very famous man, Carl Sagan. A galaxy is composed of gas and dust and stars, billions upon billions of stars. Every star may be a sun to someone. So if you're lucky enough to live in a dark sky spot, you might walk out tonight, given the weather is permitting, and see something like this. This is an image of the night sky from, I believe, an astronomy base in Antarctica, so the southern hemisphere sky. If you're in the northern hemisphere, you'll probably see something slightly different. But you'll see this faint band of light stretching across the sky, slicing through a bunch of different constellations, including Sagittarius, Cygnus, Perseus, and Orion. This patch of sky, we of course now recognize it as the Milky Way galaxy, but the ancient Greeks just thought it looked like a ribbon of spilt milk across the heavens. So that's why it's called the Milky Way. In the early 17th century, Galileo used a telescope for the first time to show that the light from the Milky Way comes from millions and millions and billions of stars. And together, those stars make up a stellar system of their own that we call a galaxy, which actually echoes from the Greek word for milk, galactos, which is why if you are allergic to milk, you can't drink milk or any dairy products, you are lactose intolerant. Galaxy is from the same root word. So this is a very, very beautiful image from Antarctica, like I said. And hopefully you'll have a chance to see the sky like this. But as always, we're going to delve into the science. And we're going to start by talking about the structure of our galaxy. So on the right, you see sort of an artist's renditioning of top down, looking at the galaxy from high above. And then the bottom is edge on, taken from the European Space Agency. So our galaxy is a spiral galaxy, named as such for its beautiful grand spiral arms. We are located in the Orion spur of the Sagittarius arm. We're nearby to the Perseus arm as well. If viewed from the side, like we have in this high-res ESA image at the bottom, we would see that the arms are part of a fairly flat disk of stars, which I've circled out here in green. This image, actually, you should imagine as wrapping all the way around your head. So the stuff towards the edges of the image are directly behind you. So we got a fairly flat disk of stars. And then there's also a central bulge. Now, if you look at the top-down image, you'll see that it's not really a spherical bulge, more like a stretched out bar. That's perfectly fine. For historical reasons, we will call it a bulge anyway. And none of these images are big enough to show the huge spherical halo of stars. Much dimmer stars, they're harder to see. But there is a huge spherical halo of stars, which will become very important towards the end of this talk. When we talk about the size of the galaxy, once again, we got to deal with light years here. Meters, we get really, really, really big numbers. Even light years, we get big numbers, but smaller numbers than if we were talking about in Earth-sized units. So we got to do galaxy-sized units. So the entire galaxy is about 200,000 light years in diameter, so 100,000 light year radius. But it is only about 1,000 light years thick. So really big, but really thin. It's like a pancake, essentially. You know, really nice, big, circular pancake, but there's not a lot of cake in that pancake. And our sun is located about 27,000 light years from galactic center. So we're kind of like in the suburbs of the galaxy. We're not at all in the hustle and bustle of the inner city, the bulge of the galaxy, and we're not out, you know, in the farmland, in the pastures of the outer galaxy. We're kind of in the middle. We're in the suburbs, which is a pretty good place to be. within our own local group of galaxies. The Milky Way is a pretty large galaxy. Only the Andromeda Galaxy is comparable in size to the Milky Way, about 220,000 light years across. And it has its own system of satellites. In fact, Andromeda and the Milky Way are so massive that they do have their own system of smaller satellite galaxies. You can actually see two Andromeda satellites here. This thing that I'm circling with my mouse towards the bottom right of the image, and then just left of center, that bright spot. Those are two satellite galaxies of Andromeda. Milky Way has its own satellites because Milky Way is almost as large as Andromeda. And the two biggest, you can see at the bottom, are the LMC and the SMC, the Large and Small Magellanic Clouds. They're both around about a Milky Way size distance away, about 150 to 200,000 light years away. And they orbit the center of our Milky Way. And they may be even interacting with the Milky Way and with each other. We'll get into that, I think, a little bit next week or maybe the week after. These are the two most visibly closest galaxies to us, the LMC and the SMC. But there are two that are even closer, but much harder to see. We didn't discover these until the 2000s. These are the Sagittarius Dwarf Spheroidal Galaxy and the Canis Major Overdensity. It took so long for us to discover that because both of these galaxies are in the process of being consumed. They're colliding with the Milky Way as we speak. And so their stars have been stretched out across the night sky. You'll see an image of this towards the end. So they're very hard to discover until our telescopes got really, really good. But so arguably you could say those are closer, but the visible ones, LMC and SMC, are the closest ones to us. All right, let's drink that. And now let's talk about, so that's the structure of our galaxy and sort of a little context into our local group. We'll talk more about our local group next week or the week after. Let's talk about our galaxy in the detail here, starting with how stars orbit in our galaxy. Well, once again, as we look down onto the galaxy, the stars in the disk, those do roughly circular, maybe just slightly elliptical, but pretty much circular orbits. They all go in the same direction. They all are roughly in the same plane of the galaxy, much like our solar system. All the planets orbit in the same direction, same plane of the solar system. However, individual stars will actually bounce up and down through the disk as they orbit. So above, they might do a circular orbit, but if we look at them edge on, they'll just kind of do a little sine wave, a little bouncing up and down. Then bouncing up and down, well, the circular orbit part arises from just simple gravitational attraction towards the center of the galaxy. All that mass within their orbit is keeping them in a circular orbit. But local variations in the galaxy's mass, maybe as we're passing through a spiral arm, that will cause the bobbing arising from that local pull of gravity from the disk itself. So the sun does this. It takes about 240 million years to complete an orbit, which means when the dinosaurs were around, the sun was in a completely different part of the galaxy. It's absolutely insane. And it also bobs. Each bob takes the sun about 300 light years above and below the disk. It doesn't get out of the disk at all. It's still well within the disk, but it does have small variations. And those bobbing takes about 80 million years to complete one in and out loop. So I don't know where we are currently in the sun's bobbing motion, but this is certainly not something you have to worry about. We're not, escaping the galaxy anytime soon. So everything is pretty well ordered in the disk. That's where the spiral arms are. That's where all the stars do these nice circular motions in the same direction, maybe some little bobbing up and down, but everything's pretty well ordered. When we look at the other two regions in the galaxy, the bulge and the halo, that's where things are way less organized. So in the halo, just like the Oort cloud in our solar system, where comets can come in any which direction they want at any inclination, at any rotation around the center of the solar system, halo stars come from this vast spherical region. Their orbits can take them far above and below the disk in random orientations at any inclination. It's much more of a random distribution of stars and their orbits. Bulge stars are a bit more complicated. It's sort of an in-between point between the disk stars and the halo stars. And we don't know as much about the bulge stars because the bulge is further away from the halo. Halo stars can pass right in front of us in the disk. And of course, we know about the disk stars because we're in the disk. We are a disk star. But bulge stars are far away. They're 27,000 light years away. And there's a lot of dust in between. So we've either got to be really good at subtracting out the effects of dust, or we found that there are small little patches where there isn't as much dust that we could see straight into the center of the galaxy. However, recent observations have shown that it is an in-between of the disk and the halo, that there is some orderly motion. There are some stars are going all in the same direction. Meanwhile, other stars are kind of random. And so this is what gives our bulge a bar shape. And you actually see this sort of X shape in this simulated image at the bottom right. That's what creates that shape of the bar. I'm telling you all this, most spiral galaxies will also have all of these features as well. And when we want to know the mass of the galaxy, that's an interesting problem because we can really only know the mass interior to the sun's orbit. So for example, we know as we measure the sun's velocity relative to outer stars and maybe to globular clusters that are further away, we can measure our sun's velocity relative to them. And we know that the sun is orbiting our galaxy at a speed of about 234 kilometers per second, or just around 500,000 miles per hour. And knowing our sun's speed allows us to calculate the mass interior to the sun's orbit using Newton's version of Kepler's third law. I'm not going to go through that derivation, but eventually you arrive to this equation. Mass is equal to the radius, how far away from the center are you, times the velocity squared divided by a constant, big G. And we see that interior to the sun's orbit is about 2 times 10 to the 41 kilograms of mass, or in other words, 100 billion solar masses. So there's a lot of mass inside the orbit of the sun. The Milky Way has a lot of mass in it. However, to get more of the Milky Way, we've got to look further and further out. We've got to look at stars further and further out and do the same thing that we did with the sun, comparing them to distant globular clusters that aren't going to be moving as fast. We can figure out speeds relatively for stars further out from the orbit of the sun. And that tells us something interesting. Now here is what this plot is called a rotation curve. It has the velocity in kilometers per second on the vertical and the distance from galactic center in kilolight years or thousands of light years on the horizontal. You can see this weird thing. Yeah, the velocity is increasing at first as we get away from the galactic center. Stars are going to be moving a bit faster, but then it sort of plateaus around maybe around 19,500 light years. Sort of plateaus, and it doesn't continue increasing, it doesn't decrease, it just sort of stays constant. Now, if all the mass in the galaxy were concentrated towards the center, then what should happen is that stellar speed should slow the further outwards we go. This happens in the solar system. Mercury orbits way faster than Neptune because most of the mass in the solar system is concentrated in the sun. But instead, as I just pointed out, orbital speeds remain mostly the same as we go further out, telling us that most of the mass isn't concentrated in the center of the galaxy. Most of the mass is evenly distributed throughout the galaxy in what we are assuming is the stellar halo. This, as we'll point out in a few more weeks, is evidence for dark matter. We'll talk about that much later. Now, our Milky Way is our home galaxy, but its importance to our existence runs much deeper. Essentially, the birth of our solar system couldn't have occurred without this galactic recycling system that takes place within the disk of the galaxy and its interstellar medium. Now, galactic recycling makes new generations of stars possible and gradually changes the chemical composition of the interstellar medium. So let's talk about how this recycling happens in the galaxy. And we'll start with stuff that we've already talked about, the birth of stars. So remember that stars are born in collapsing molecular clouds that as they collapse under their own gravity, they fragment into different portions. The temperatures in those fragments will reach around 10 million Kelvin for where hydrogen fusion can begin. And so we got a star, and that star will fuse hydrogen into heavier elements, maybe only up to carbon if it's a low mass star, maybe all the way up to iron if it's a high mass star. And we'll do this for between millions and billions of years, depending on the mass of that star. Where the high mass stars will survive for only millions of years, the low mass stars will survive for billions and billions of years. And when they die, many of them will either scatter out, will expand their outer layers and form a nice planetary nebula, or maybe if they're a high mass star, they will go supernova and scatter their chemically enriched guts across the nearby interstellar medium. So on the left here is the Cat's Eye Nebula, a beautiful, beautiful planetary nebula caused by a low mass star blowing out its outer layers. On the right is the Bubble Nebula, which we believe is a star that has gone supernova. This is the sort of the remnant of the star. And that shock front is moving further out. Just as I mentioned, these supernovae will generate these shock fronts. These are essentially just high pressure, high gas pressure walls that sweeps out and pushes out the surrounding gas, exerting some force, but slowing down until eventually it stops and merges with the surrounding interstellar medium. Spreading those chemically enriched elements throughout the nearby portion of the galaxy. And this gas is often hot enough to emit X-rays. And so we can easily see where supernovae have happened in the recent past through X-ray telescopes. And doing these sort of observations have actually shown us that we live in a bubble like this, creatively called the local bubble. It extends about a few hundred light years. Now, we were not created in this bubble. We are moving through the bubble. We entered it a few 100 million years ago. We'll exit in another few 100 million years. But clearly, a star went supernova in our position several million years ago. One of these beautiful supernovae remnant is the huge Veil Nebula. Oftentimes, this image is not one image. This is a mosaic of many images because this is so stretched out across the sky that you got to do many images to even get the full picture of it. But these are all shock fronts. Slowly, the Veil Nebula is merging with the local interstellar medium, returning those elements that star that created the Veil Nebula, returning those elements that it created in itself to the galaxy. Now, in certain parts of the galaxy, we will actually see these huge cavities that are more than 1,000 light years across, larger than the normal bubbles caused by just a single supernova. So we think these super bubbles were formed from the merging of several smaller bubbles. And these super bubbles can continue moving out and will oftentimes actually just break out of the disk. These are thousands of light years across. The disk is only 1,000 light years thick. So it will actually break out of the disk. And suddenly we got gas erupting from the disk of the galaxy. Because there's nothing to stop the gas from escaping. We've run out of interstellar medium as we move out above the disk of the galaxy. And so we get all this hot gas erupting from the disk, spreading outwards as it shoots upward. We call this whole mechanism the Galactic Fountain. We have seen a few nearby in our Milky Way galaxy. Of course, we can't see the other side of the galaxy. There's too many stars and dust in the way. I think we've seen them in the Andromeda Galaxy. They're actually patches in the Andromeda Galaxy. There isn't any gas. We think that was caused from a galactic fountain event. But eventually, we're pretty sure that this happens around the galaxy. That's just a guess. It's hard to verify because all we see nearby is the hot gas expanding outwards above us and cool gas raining down back into the galaxy, both from above and from below. We're pretty sure this happens all over the galaxy. Now, once this hot gas in the superbubble either cools or rains back down on the galaxy, then it will rejoin the atomic hydrogen gas that makes up most of the interstellar medium. And we are able to see this atomic gas through its radio emissions. Atomic hydrogen works because it got just one proton and one electron orbiting the proton. An electron can either be spin up or spin down. And every time it randomly transitions from one to the other, it will emit light of a particular wavelength. And that wavelength sits well within our radio wavelengths at 21 centimeters or 1,420 megahertz frequency. And so we're able to see this atomic gas, and we are able to measure its mass. The total amount of atomic gas in the galaxy, we believe, is about 5 billion solar masses. And atomic gas will come in two different forms. Either we got large, tenuous clouds of warm gas, about 10,000 Kelvin, or smaller, denser clouds of cool gas, about 100 Kelvin. Most of it is in the warm phase. So it's very sparse, spread all throughout the galaxy. And this is one of the pit stops for this kind of galactic recycling process, because matter will just stay in this atomic gas for millions and millions of years until gravity finally starts to get a hold and start to slowly contract blobs of that gas. Eventually, it will all cool well enough to form molecular clouds full of molecular hydrogen. And eventually we'll start to form stars. And we repeat this process all over again. So it's this whole big, nice star gas star cycle that create stars. The stars will create the heavy elements. Then they will explode or scatter off their outer layers, spreading all of those heavier elements throughout the galaxy in the form of bubbles and super bubbles, maybe even a galactic fountain or two. Then that will get put back into the gas that makes up the galaxy, which will slowly cool, forming molecular clouds, forming stars again with those elements, making more metal-rich stars as time goes on. And we can see this process happening when we look at the galaxy in all the different wavelengths. So here's a beautiful NASA image of the multi-wavelength Milky Way. We've got high wavelength, low frequency light up at the top, and low wavelength, high frequency light at the bottom. So we've got radio waves. The atomic hydrogen is the second one from the top. This is the warm gas clouds. You can see how confined it is to the disk. It's not getting very high up or very well below the disk, except towards the outskirts where there's less of a hold. Then the fourth one is the molecular hydrogen, which we trace by looking for carbon monoxide. And we just assume wherever there's carbon monoxide, there's molecular hydrogen. And that's a big assumption, and people are worried about it. But we also see that it's mostly held to the disk. All the stars are going to be forming in the disk. Maybe there's some more cloudy stuff on the outskirts, but most of the stars are going to be forming in the disk. Then as we get into the infrared, the far, mid, and near infrared, we are seeing in the far and the mid where the dust is in the galaxy. The dust is especially confined to the disk. Maybe there's some more dust above and below the disk. In the near infrared, we're seeing nothing but the starlight. We can see through the dust in the near infrared. We learned about that a few weeks ago when I was showing you that those clouds of really dense dust and how they just became more invisible as we viewed into more infrared light. So here you don't even see any of the dust. You see nothing but stars. You see a huge kind of X-shaped clump where the bulge is of our galaxy. You see the disk. In the optical, of course, we're very familiar with the optical. We see the different dust lanes. We see all the dust clouds, maybe some star-forming regions. And then as we get into the X-rays and gamma rays, in the X-rays, we see all the hot gas from where those supernovae occurred. In fact, this big blob, that is where a supernova occurred. I believe it's the Vela remnant, not the Veil Nebula, but the Vela, V-E-L-A remnant. So maybe some more supernovae towards the right, maybe there's some towards the left. And then on the gamma rays, we see cosmic ray collisions. There's definitely some gamma rays being generated from the Vela remnant. some gamma rays being generated towards the center of the galaxy. I wonder what could be causing that. You can see all of this. It is always very useful to look at different wavelengths of light when you want to learn more about a galaxy. In fact, that's what my research does, not for the Milky Way, but for different galaxies altogether. So now let's talk about where stars are forming in our galaxy. So near hot young stars, where they're so hot, they're actually ionizing the gas around them. Usually, there's still tons of gas because the stars formed relatively recently and all the gas isn't blown away yet. We'll actually find that the stars are ionizing the gas around them. And so we get ionization or emission nebulae, where the ultraviolet light from those young stars have ionized the nebula, causing the gas itself to emit light. So one great, very well-known example of an emission nebula is the Great Orion Nebula, known as an SCA 42. And you can see, I've mentioned it a lot, how astronomers don't look at those beautiful rainbow spectra. We look at just plots of line plots. But here they put the rainbow and the line plots together. And so you can see the colors in the Orion Nebula. All the reds you see are created by atomic hydrogen that is being ionized. All the nice kind of blues and purples you're seeing are caused by ionized oxygen in the blue and ionized oxygen in the nice magenta purple. There's also some hydrogen, the lower Balmer lines, causing some deeper, some royal blues, some more cyans. Maybe there's a bit of yellow in there too, caused by ionized helium. That's all what you get from an emission nebula, like the Orion Nebula. Meanwhile, if you see a nebula that is more of instead of this nice bright blue, bright red tint, you see kind of a darker, eerie blue, maybe some black tints, that is actually called a reflection nebula, where it is dust that is absorbing the red light from stars and reflecting the blue light. So on the left is the Witch Head Nebula. You might be able to see the witch's head in that shape, where it's blue because nearby, just off the picture, is the bright red star Antares, seen in the eye of the scorpion, Scorpius. And so it's absorbing all that red light. The dust is absorbing the red light from the red giant Antares and reflecting off the blue light. That's why the witch's head appears blue. Here on the right is NGC 1999, where this big bright star here is emitting a lot of light. This dust surrounding it is absorbing the red, re-emitting the blue, and is giving us this nice kind of eerily blue. Now, what's really eerie is this big blank spot. Astronomers found out recently that's not just a really compact dust that's absorbing all of the light. That is actually just an empty hole in the gas cloud. We're not sure how it's created, but it certainly does give this image an eerie feeling, I believe. Now, where are all of these star formation sites happening? These emission nebula and reflection nebulae? These are happening in the spiral arms. So here's a beautiful image of the interacting galaxy, the Whirlpool Galaxy, where the Whirlpool, SCA 51, is sitting here on the left and is interacting with its companion on the right. You can actually see one of the spiral arms stretching all the way to the companion. These spiral arms are the home to all of those molecular clouds and those young star clusters surrounded by emission nebula. In fact, as you look at the Whirlpool Nebula's arms, the Whirlpool Nebula, the Whirlpool Galaxy's arms, you see all these big red spots. Those are all star-forming sites. And Whirlpool Galaxy especially is going through a huge burst of star formation as it merges with its companion galaxy. This is actually a known effect called swing amplification, where its spiral arms actually get much bolder, do a lot more star formation, and are much easier to see. This is a process that happens with interacting galaxies. So here we see these hot blue stars. You see the spiral arms have kind of a blue tint to them. Those are the hot young blue stars that emit a lot of light. And these red ionization nebulae are tracing out the arms. While the stars in between the arms, if you look at the interarm regions, you see that they're generally redder and older. There's still some star formation happening in the interarm, but they are generally redder and older, not doing as much star formation as the spiral arms. And we also see this molecular and atomic gas. These dark dust lanes are on the inner edges of the spiral arms. And certainly there's a lot of dust, a lot of molecular clouds in between the two galaxies, where there might be a lot of star formation in the future, a lot of new stars in the future, I should say. So that means that spiral arms contain both young stars and the material to make more. So that star-gas-star cycle is really a feedback loop. It has all the material necessary to make more stars and keep itself going. Now, what are these spiral arms? Well, that was a big question for astronomers in the late 1800s, early 1900s. Just exactly what were they? Is the entire galaxy rotating? Are these another phenomenon? Thankfully, in the 60s, we think we figured out the answer. So we think spiral arms are caused by what are known as spiral density waves, which essentially causes stars to pack closer together to form the spiral arm and then spread apart in the interarm region, just like a traffic jam on the interstate. So if you're from Atlanta, or if you're from another city that has a loop, an interstate loop around it, so in Atlanta it's I-285, the perimeter, then you know that sometimes you just slow down on the interstate for no reason, like there wasn't an accident, it's not rush hour, you don't know why you're slowing down, and then you just sort of gradually speed back up again. That's actually a density wave traveling backwards through the interstate, causing cars to slow down and then speed back up again. Same thing happens in galaxies. So on the left is an animation of maybe the entire galaxy just is a solid body. The arms are actually rotating with each other, rotating as a physical thing. Well, that doesn't really make sense because the stars in the middle would be rotating slower, would be orbiting slower than the stars on the outskirts. And we just talked about that nice rotation curve where all the stars are pretty much going the same speed. So that's not going to fly. Maybe the stars themselves are generating these spiral arms. Maybe it's being tightly wound. Maybe it's being wound up. But if they do that, then the spiral arms get more tightly wound as time goes on. And instead of these beautiful grand design spirals we see, we're going to get something that just looks like a disk with maybe some rings. Maybe eventually it'll just kind of blur out to be a very smooth disk with no spiral features whatsoever. That is not at all what we see. Instead, what we see is those spiral density waves. Or if you look at this last animation, you see the stars moving in and out of the spirals. And the spirals, it's sort of an optical illusion. They look like they're moving, but they aren't. They are in the same spot. So the spirals are not moving with the galaxy. They're not rotating in themselves, but the stars are moving in and out of these spiral density waves, just like a traffic jam on the interstate. There's a lot of math that goes into describing those spiral density waves. Now, when we talk about the stars of the galaxy, we can break them down into two different stellar populations. We call the stars in the disk population, or population 1 stars, POP1, you might hear astronomers say. These are the stars that are going to follow those orderly orbital patterns in the disk. All are going to be rotating the same way, say lying in the plane of the galaxy. Maybe there's a little bob, but essentially the same plane of the galaxy. They're also going to have a wide range of ages. They might be formed relatively recently, be very young, hot, blue-white stars. Maybe they formed a long time ago, and they're just those dim red dwarfs. They're going to have a wide range of ages. And they're going to have a bit of metals like the sun. The sun is 2% metallic. And remember, to astronomers, metal is anything that isn't hydrogen and helium. So the stars of the disk are going to have a little bit of metals sprinkled in them, just a little bit of spice, a little bit of kick. Then we can talk about the halo stars, the halo population, or population 2 stars, POP2 stars. These are the ones that are going to follow those haphazard orbits, just like the Oort cloud comets in the solar system. These also won't have a wide range of ages. These are all going to be pretty old, around the age of our galaxy, and won't have that extra kick of metals. They're going to be pretty much just hydrogen and helium, very few metals lying within them. So you can think of the POP1 stars, those disk population stars, very similar to the stars that are forming in those emission nebulae, in those young clusters. So just like this young cluster in the Small Magellanic Cloud, AGC 346, nice, beautiful emission nebula. There's a star cluster in the center, forming nice young stars, but interspersed in a mix of older stars with a bunch of different metal content. The halo population, the POP2 stars, you think of it as a globular cluster, like Messier 80 here, where most of it is just sort of red old stars, not many metals, not much activity happening. And globular clusters are stuck in the halo of the galaxy. So they're going to have random orbits at different orientations at different directions. We can explain this by noting that the halo doesn't have any of that gas we just talked about. The disk has all of the atomic gas and the dense molecular gas that's necessary to form stars. That explains how we have both young and old stuff. The halo doesn't have any of that gas in it. So the halo only has stars that formed a long time ago, and then it hasn't been able to do any star formation since. And the lack of metals indicates that the stuff in the halo was formed before there were many supernovae in the galaxy, indicating that it formed a long, long time ago. And then in the disk, a bunch of supernovae happened and polluted itself with metals. The halo doesn't have access to any of that. So how do we explain all this when we talk about the formation of the galaxy? Well, actually, we can sort of get an idea of how we explain it by talking about how we explain stars again. Remember, stars were formed from collapsing molecular clouds. Same thing with the galaxy, and the simplest model, at least, is just a collapsing proto-galactic cloud that we've got hydrogen, helium, and a lot of dark matter. Now, early on, gravity would have drawn in this matter from all directions, creating sort of just this kind of a spherical blobby cloud that eventually would fragment, just like molecular clouds forming stars do. And those stars that formed this early on could have orbits with any orientation. They're going to do whatever they want. But as time passed, as gravity continued collapsing this big, giant proto-galactic cloud, as we all know, the law of conservation of angular momentum would have eventually started this whole gas cloud spinning, condensing it not into an even smaller spherical cloud, but instead a spread out disk. And that ensured that all of the gas was trapped in that disk. And it all would have been rotating the same way. So stars that formed after this point would have had orderly orbits, and they would have had access to all of the gas in the disk, so they could continue to form, polluting itself with metals, and making stars that are not only old, but also very young. And so through this scenario, we've explained both the ages and the metallicities of the disk and the halo stars. If only it were as simple as this, though. This sort of monolithic collapse model does explain those general properties well. But as we've studied the disk and the halo stars to more and more detail, we found that this sort of thing is really too simplistic. So we do find variations in the metallicities of all the stars, the disk and the halo stars, suggesting that the galaxy's oldest stars actually formed in smaller proto-galactic clouds that later collided and merged and combined and got all mixed in with the Milky Way. So the halo stars did their own thing somewhere else and then eventually merged and joined with the Milky Way. We can animate this. These are some great animations. So on the left, which we'll play first, it's just a single accretion event. So we've got the Milky Way, the disk in blue. Here's this blob of stars that are going to come in from the side and merge with the disk. And you see as it orbits, if it eventually falls into the disk, its stars get stretched out, pulled apart. It's no longer a blob, but instead a stellar stream of stars that will wrap itself around many, many times before its stars finally fall into the disk and become part of the Milky Way. And that looks really cool, but we did not go through just one accretion event. We went through several, so we can simulate that as well. So here's many globs coming together of different sizes. You see some of them pass straight through the center and scatter outwards. Some of them are coming on more inclined, more stretched orbits and are able to survive a bit longer. But what we get at the end of this is sort of a spherical distribution of stars outside the disk and a bunch of stellar streams as different clumps of stars are being eaten by the galaxy. And this is exactly what we see when we go out and look at the night sky with our great telescope. So in 2006, with the Sloan Digital Sky Survey, we looked at these stars as a function of distance, and we found streams all over the place. This is how we found that Sagittarius dwarf spheroidal galaxy. Here you can see the Sagittarius stream stretching across the skies in the northern hemispheres, but you can also see a bunch of other things. So here's another stream, Palomar 5. This is actually a globular cluster where stars are being ripped off of itself as it travels too close to the Milky Way. A cloud, the Hercules Aquila cloud, maybe some other streams, the Orphan stream. There's a Monoceros ring. All these circles are new dwarf galaxies that are further out, or maybe some globular clusters. We see this all over the place. This is exactly, the theory is matching the observations, which is what we love in science. We do see the remnants. It's not even remnants. This is currently happening. The Milky Way is still doing stuff like that. So we've reached the far outskirts of the galaxy in the halo. Now let's zoom back in and travel to the center of the galaxy. So at the center of the galaxy lies towards the constellation of Sagittarius. If you're looking at the constellation of Sagittarius, you're looking towards the center of the galaxy. As you can see in this set of zoomed in images. And as we look towards the center, we see millions and millions of stars. We see extremely turbulent gas and this weird radio source, which we've creatively named Sagittarius A star. Now, as we look towards Sagittarius A star, we see that there are several hundred stars stuck in just a region a light year across around Sagittarius A star. And as we watch their orbits, it actually indicates the presence of an extremely massive object. Here are its orbits. Those stars are moving on human timescales over years, which is not what we're used to. As we talked about last week, this thing we're calling Sagittarius A star is actually a black hole, a supermassive black hole in the center of our galaxy, a mass of about 4 million solar masses, all packed into a region of space a little larger than our solar system. But that's what's at the center. That's sort of the end for now about the Milky Way. We'll take the lessons that we've learned about the Milky Way and generalize them next week to all different types of galaxies as we start our view of galaxies and our view of the universe and cosmology. Now, as I keep saying, we're doing astronomy. You can go outside and look at things we're talking about. Hopefully, you have access to a dark sky spot. You actually go see the Milky Way. However, if you're living in a city like Atlanta or like Cleveland, then you probably will not be seeing much. This is an extremely light polluted sky. Perhaps you will be able to see, hopefully you'll be able to see Jupiter and Saturn. They are reaching their closest approach to Earth in August. Jupiter's has already happened. Saturn is going to happen in the coming days. So they'll be pretty bright in the night sky, rising shortly after sunset. You might even be able to see the summer triangle, this connection of 3 stars here, Vega, Deneb, and Altair. I got there eventually. Part of 3 different constellations, but together they form a summer triangle that is above, directly overhead all summer long. Now I'll play this little movie I made and we'll move to even darker and darker skies. You obviously can't see the Milky Way here, but it is there, just too overshined by city lights. I'll play this little movie and we'll move to even to darker and darker skies. And hopefully you'll be able to see the Milky Way emerge, as well as many, many, many more stars. So at the darkest sky spots, not only all the stars appear much brighter, you finally see Arcturus and Antares. You also see the beautiful band Milky Way. Down here is towards the direction of Sagittarius. This is simulated for about 10 o'clock, 10:30 tonight, though it'll probably look the same any night this week. You see the Big Dipper there. You even sort of make out a Little Dipper here. There's Polaris. Here's Cassiopeia. Hopefully you are near a dark sky spot. There's a lovely website, light pollution map or something. You can Google it. That will show you a map just like this, where all of the light pollution is. So if you're living in the eastern United States, you're kind of out of luck. Myself here in Cleveland, I am more in luck though. There are a few places nearby. You go to the mountains of West Virginia or maybe the Allegheny State Forest in Pennsylvania to get some darker sky spots. If you're viewing this from Georgia, then you better go join the alligators down in the Okefenokee Swamp. That's going to be your only sure bet to get a really nice dark sky spot. If you're in the western United States, especially in the plains and then in the desert, as long as you're not in a big city, you are in a dark sky spot. Travel out towards Area 51 from Las Vegas, and you will be in a nice dark sky spot. If you're on the California coast, hopefully you're in the northern coast, nowhere near LA or San Francisco. And if you're in the Northwest, you got to travel into the Rockies a bit. If you're in Canada, you're in great luck. You just got to get out of the city. But definitely go play around with this. It's a great site. Europe is just completely out of luck. There's no dark sky spots in Europe. But hopefully at some point in your lifetime, you'll be able to travel to a dark sky spot and go see the beautiful Milky Way stretched out overhead. So that is it for tonight. Next week, we will talk about galaxies and modern cosmology, and then move on to galaxy evolution and then on to the universe. But we are running out of topics to talk about. So we're nearing the end here, guys. It's going to be real sad. So as always, like, comment, subscribe. Let me know if you have any questions. I'd be happy to answer them. And I will see you all next week.